The next keynote speaker, I am privileged to announce Professor Krishna Reddy. Krishna Reddy. We will read the brief bio. Professor Krishna Reddy is a professor of civil engineering, civil and environmental engineering at the University of Illinois, Chicago, USA. He is also the director of the Sustainable Engineering Research Laboratory and the Geotechnical and Geoenvironmental Engineering Laboratory. He received his PhD from the Illinois Institute of Technology, Chicago, USA. He earned gold medal in his BE Civil Engineering at Osmania University, Hyderabad, and in ME Geotechnical Engineering at IIT Roorkee. With over 30 years of experience, Dr. Reddy's work spans geotechnical, environmental, material, and sustainable resilient engineering, addressing the nexus of infrastructure, water, energy, and the environment. He has authored 4 books, over 300 journal papers, 44 edited proceedings, 27 book chapters, and 279 full conference papers. He serves on editorial board of over 10 journals. He has received major honors including the ISSMG Carey Rowe Lecture, ASC Wesley W. Honor Award, ASTM Hogan-Stogler Award, and the UIC Distinguished Researcher Award. He is a fellow of the American Society of Civil Engineers, ASC, a registered professional civil engineer, PE, and an Envision Sustainability Professional, ENB, SP. So, sir, please take the
Good
stage.
afternoon, everyone. First of all, I want to thank organizing committee for giving me this opportunity, and I want to thank you all for being here. And I looked at the theme of the conference and then decided to talk about sustainability. And you see my title is Selecting Sustainable Geotechnical Solutions, Quantitative Assessment-Driven Approach. I know there's going to be a special issue of Indian Geotechnical Journal with all the keynote papers. So I submitted this paper, and fortunate that it has come out before my presentation, and I tried to publicize it as much as I could. It is a long paper, 27 pages. So what I'm going to do today, within the short period of time that I have, just about 20 minutes, 25 minutes, I will give you a brief overview of it. So when you go back and read it, you will have a better appreciation of the content. However, I will be here all day. So if you have any questions, if you want to discuss anything, I will be very happy to answer your questions. So what is that we are talking about? What is the problem, right? Currently, geotechnical engineering, or in general engineering, is based on codal requirements or regulatory requirements to ensure that it is safe, right? So that's we are familiar with it. And then when you have multiple options, what we see is what is the option that is easy to construct and what is going to cost less, right? And then which option takes less time for construction. So these are all the considerations that we make in selecting a design. So there is no problem with doing all these things. However, we don't consider these following factors. One is we don't consider the sustainability, we don't consider the resiliency, we don't consider the life cycle thinking. So if you consider all these things, actually you can create innovative solutions, and that are going to be sustainable and economical. So sustainability is a buzzword used by everybody, right? Is there anybody that doesn't know or doesn't hear about this word sustainability, right? And I asked the same question in other conferences. All the hands, were raised. So this is a buzzword. Everybody, uses this word sustainability, whether they know anything about it or not. But it sounds really good, right? So what is sustainability? There are many definitions. In one of my papers, I have given more than a dozen definitions for sustainability. So this is the common definition that people use, United Nations Bernland Commission definition, meeting the needs of the present without compromising the ability of future generations to meet their own needs, which is very good, very succinct, very powerful, but it doesn't tell us what to do in order to achieve this goal. So we modify this definition basically by adding, to achieve this goal, you need to balance between environmental care, societal well-being, and economic growth. So this one, you are probably familiar with triple bottom line. So if you can address the triple bottom line, you will be able to address this broader goal. So why are we talking about sustainability a lot compared to a few years ago? Because of these drivers. All these things are getting worrisome year after year. These are not like a temporary things. We are depleting the natural resources, and the environmental pollution is growing, population is increasing, waste generation is increasing, greenhouse gases are increasing, we have a declining ecosystem, loss of biodiversity, social injustice, urban sprawl, and so forth. These are worrisome as we go into the future. So the sustainable development is not possible unless we address these things now and into the near future. Now, other buzzword is resilience, right? So again, everybody uses the word resilient, resiliency. So yeah, this is also a very, a fashionable word to use in papers, in theses, in conferences, and all those things. And this also has many definitions. Again, in one of my papers, I gave more than a dozen definitions what resiliency is. So ASCE defines the resiliency like this, right? But I have just modified that one. Resiliency is the capacity of a system to prepare for and overcome unexpected crises and adapt to turbulent changes. Those can be, these unexpected crises and turbulent changes could be anything. Recently, a lot of emphasis on climate change impacts, but that could also include some of the hazards like earthquake engineering, earthquakes that we are talking about. But this is what we don't do. As engineers, we try to make the technical design to be safe under these turbulent or changing conditions, but we need to optimize it in such a way that we will have a minimum possible impact on the environment, social, and economic. So this is what I mean in this figure. You see the center part is the technical part that makes it the system to be functionable, but we should not have any cascading negative environmental impact, cascading negative economic impacts, cascading social impacts, right? If you want to design for something that is going to be expecting in the future, you have to be very conservative design, and then that is going to cost a lot of money if that impact could happen or not happen. So it's balancing these factors in designing your technical design that can be safe under expected shocks or changing conditions. This is what the resiliency is. As I told you, earthquakes, of course, has been a problem, but what we are worried too much about these days is the climate change impacts. Climate change and extreme weather impacts are happening, and as a result of that, we see a lot of damage, right? Even in your neighborhood, you could probably see these kind of things happening, disastrous impacts that are happening. And these impacts are increasing year after year, right? So we cannot really sit tight and not do anything. So we need to be doing something to address these issues. Flooding, for example, I'm from Hyderabad, and we never heard about Hyderabad getting flooded, right? But now that has become a big problem, and so next time when you build something in Hyderabad, you need to think about the flooding scenario that could happen, right? So the sustainability and the resiliency, and the other thing is the life cycle thinking. A lot of our engineers, especially civil engineers, they don't think about this life cycle. They think about, okay, we design, magically, materials are going to appear, we construct, and then perhaps monitor it. That's it. But if you really want to think about this life cycle concept, you need to be thinking about resource extraction, where the resources are going to come, and the materials manufacturing, how they are going to be manufactured, and then you're going to construction, and then you have to look at the maintenance, and you should also look at what is the end life. It could be 50 years or 100 years, whatever it is. Future generations have to consider demolishing that structure and then rebuild it or build new, what are they going to do with the materials and other things? So we need to think about all these things. So this is called life cycle thinking, and you must consider the sustainability and resiliency through the entire life cycle. Each life cycle stage you need to consider. So that's why this is called life cycle, sustainability, and resiliency. So we should be looking at all these things. So this life cycle assessment, for example, if you look at ISO 21930, that talks about, EPDs, if you are familiar with this one. So they divide the production stage, same thing, life cycle. So A1 to A3, construction stage is A4 to A5, usage stage is B1 to B7, and end of the life stage is C1, C4. So you will, if you are familiar with, materials, EPDs, that kind of things, so you will see this terminology in that. So I want to just mention that sustainability without resiliency, you're making the engineered system that is vulnerable to climate change. So there is no point in looking at, the system because, under expected short-term conditions, it's not going to survive. So what is the point in looking at the long-term sustainability considerations? Resilience without sustainability is also not a good thing, because if you want to make it more resilient, if you are using carbon-intense materials or other things, then it's not good. So resilience and sustainability have to be combined together, right? So therefore, we need to have a sustainable and resilient engineering solution. So this is very important, not only in geotechnical engineering, in any engineering in general. So what is the current practice? What is the current practice? I say greenwashing. Have you heard about greenwashing, the term greenwashing? Right? Haven't used it? So this is the greenwashing is wrongly portraying a project, product, or service as a sustainable and resilient than it truly is. It's basically publicizing it in a wrong way. You know that your material, your product is not good, but you say that it's good, right, in marketing terms. So that's called greenwashing. So this misleads the public and stakeholders. This slows the true sustainability progress, undermines the trust, hinders innovation and policy. So that's what is happening now. People, call their solutions, their materials or their products sustainable, but in fact, they may or may not, right? So it's ethically wrong. So how do you say that it is sustainable? How do you say that you're not doing the greenwashing? That requires you to quantify the sustainability. You need to quantify the sustainability, then you say that it's sustainable. Just don't say that it's sustainable, it may be not sustainable. So the essence of sustainability is embedded in this triple bottom line. This is environmental, economic, and social. I know everybody knows this one, but to quantify each of these pillars, you need to have indicators. The indicators have to have metrics. For example, for environmental aspects, carbon footprint is the one that is used as an indicator. You probably heard about carbon footprint, right? So carbon footprint is one of the indicators. So carbon footprint is low, that is more sustainable. Carbon footprint is high, that is not sustainable. So carbon footprint basically represents the greenhouse gas emissions. But carbon footprint is not the only environmental impact, right? You will have all these other environmental impacts. So in order to have a true environmental sustainability, you need to consider the carbon footprint as well as other environmental impacts. And we need to quantify these indicators. To quantify these indicators, we need tools. And one of the tools is the carbon footprint calculators, right? So you probably heard about this carbon footprint calculators. And everyone should, if you are working in sustainability, you should know basics of how to calculate carbon footprint. If you don't know, this is the first thing that you need to learn, in the field of sustainability. It is all about, what are the greenhouse gases that are generated, and each greenhouse gas has the global warming potential, and combining them through the GWP, you can get the carbon footprint. So it's a combination of all the greenhouse gases represented in one single value equivalent to carbon dioxide. So I really want you to know how to calculate these things. And there are a lot of examples, in one of the books that I mentioned. And then you talk about embedded carbon. So what it takes, what is the carbon footprint of making a particular material? If you have a steel, you have an embedded carbon. Concrete has embedded carbon. So any material that you think about, you could look at an embodied carbon, basically carbon footprint necessary to produce that material. And you hear about these tools, right? So DFI is very, very aggressive in promoting their calculator, DFI carbon footprint calculator or carbon calculator. There is a tool called EC3. IGS, International Geosynthetic Society, is also very aggressive in terms of promoting their sustainability calculator. So these are all carbon footprint calculators. And I want to give you examples, right? So you have options. So if you want to do the pile load testing, here are the two options. One is the bidirectional test. Basically, this is the Osterberg load testing, load cell testing. Basically, you put a load cell here, and you load it, and then you can get basically the results of load capacity. Conventional way is this, right? The support system, loading, and all those things. So if you do the carbon footprint analysis, just because you don't require the additional height of the pile for the sake of pile load testing compared to the final elevation of the piles, you can save, so much of carbon footprint. That's one thing. So then you have additional carbon footprint reductions due to reduced transportation of the materials that are required for this conventional testing. Here is the decision that you're making. Based on the carbon footprint, my first option is the better option. Here is the second example. Let's say I want to have a design of piles. So the shape of the pile is very important. You can design to get the capacity that you want. For example, I want to get a 4 meganewton capacity. So I can use these different shapes. I can get the capacity that I want. For each of these cases, I can get the same capacity. But which one is better? Because of the less material that is used, you will see that different ones will have a less carbon footprint. So out of this one, if you look at it, the option is hollow tapered one has the lower carbon footprint. Now it has the same design. All of these have the same design capacity, but here you're optimizing the shape to reduce the material, and as a result, you're reducing the carbon footprint. So if you say that tapered one is sustainable, I would not believe you. If you run these numbers, if you show these numbers, then you can believe it. MSC wall design. For example, option one, you have a reinforcement, steel straps, conventional concrete, and backfill the transportation distance is 50 kilometers. If you have an alternative, geosynthetic straps, ultra low carbon concrete, and 20-kilometer distance, this option two will have a 40% reduction in carbon footprint. You can calculate it and show that one. Now I can say the option two is more sustainable than option one. This quantitative assessment is extremely important to rationally say one option is more sustainable than other options. Now, just a simple carbon footprint calculation is not, it's not easy. There are a lot of challenges. I'm not going to go through these challenges, but I want you to be aware that, carbon footprint analysis also has to be done carefully. The major limitation of the carbon footprint analysis is that you're getting only carbon footprint. What about other environmental impacts? Remember, I told you that if you want to truly consider the environmental sustainability, carbon footprint is just not enough. You need to be looking at other environmental impacts. If you want to look at the other environmental impacts, the most common tool that people use is called life cycle assessment. I know this is used to be taught in other departments, but now it is being taught in every department, in civil engineering departments also. So life cycle assessment is a standardized procedure. ISO 14040 is the one, and we have these 4 steps that you have to follow. And there are a lot of databases that give you the information, and there are a lot of impact assessment methods. So you can have a course on life cycle assessment. There are some computer tools, like computer software, like CIMAPRO, Gabby, that embed all that databases, and they all embed impact assessment methods. So it's kind of very easy to use. And when you use the LCA, depending upon the impact analysis method that you're using, so you get all these indicators. Look at this. In this one, this is the other one. if you use a different impact assessment methods, you get all these indicators here. And also you can get endpoint indicators. The point I'm trying to say is the global warming. Global warming is the carbon footprint. You get the global warming, carbon footprint, plus you get other environmental impacts. Same thing here. If you, depending upon which impact method you're using, global warming is one of the environmental impacts. So please take away this point, because if carbon footprint alone is not environmental sustainability, it does not reflect the total environmental sustainability. If you are just using the carbon footprint like DFI or IGS sustainability carbon footprint indicator, that's not a truly indicator, environmental sustainability indicator. You can do this example, and I'm giving you case studies because that way you can understand all these different scenarios. So here is the building. You can punch in, you can input all the materials, and you can look at the impacts from different components of the project. So here you are not doing alternatives. For the building, where are the environmental impacts coming from? The first one is the carbon footprint. That's a carbon footprint. And you can see, in this one, this green one is the one which is contributing a lot. That means there are steel piles. The steel piles are contributing significantly to that one. And then you can look at other environmental impacts here, and you can see, can we do something to reduce the steel piles in this structure, or in the future, to reduce the overall environmental impacts. So this is another case study. So for the liquefaction mitigation, you have these different options. Here is the jet grouting. Here is the cement stabilization. Here is the geogrid. Here is the extension of quarry run trench. So all these options can mitigate the liquefaction. But which one is more sustainable, right? And in this case, you run this life cycle assessment, and you look at these options, option 1, option 2, option 3. The first one is the carbon footprint. If you are just looking at the carbon footprint, the lowest one is this option 3. But you also need to look at other environmental impacts. In this case, consistently, option 3 has the lowest environmental impacts. So therefore, option 3, using the geogrid, is environmentally sustainable, right? And then here is the landfill cover system. You have a traditional drainage layer. Other one is the geosynthetic drainage layer. Again, you can run the LCA analysis. You can get the carbon footprint as well as other environmental impacts. And holistically, you can say which one is more sustainable. Again, LCA requires very careful way of doing it. So here are the challenges. But the main limitations is, environmental impacts. What about economics? What about social? In economic sustainability, you need to look at all these things, indicators. What is the cost, direct cost, indirect cost, direct benefits, and indirect benefits. Here are the tools to use it. So here is the option. You have a retaining wall systems, right? So this option, first one, is carbon footprint reduction is less, and economically it's also cheaper. So here is the challenges and the limitations, right? So you need to be environmentally sustainable, economically sustainable, but also this factor that a lot of people ignore is the social, sustainability. And this is where how the project is going to be benefiting the community and benefiting the environment. So it's kind of communities and persons individually. So here are the tools that can be used to assess the social sustainability. So just showing you these options. You can do all kinds of projects like this. In the paper, I give you all this information. But what happens is when you do the LCA analysis, in this case, so if you look at the climate change or carbon footprint, so one option is more sustainable. But the results are not consistently lower for that option. So other option is environmentally sustainable for another option. So you will have a conflicting results for the both options. This is where you need to look at the multi-criteria decision analysis. So you need to look at the economics, you need to also look at the social indicators, and then you look at the ratings and see which one are sustainable. So you can do all these things. I just want to mention that my point of presentation is just say sustainability. My system is sustainable. Don't say, it is resilient. Show me with the numbers. Use the quantitative framework, and then you can convince anybody for, again, sustainability and resiliency have to be integrated. And, these tools are being developed now. Everybody is being taught through short courses. In universities, you have regular courses. For example, remediation. We have the soil remediation options, groundwater remediation options. Which one are resilient? You can do the resiliency assessment and get a resiliency indicator. And groundwater, what is the options? And combining the resiliency and sustainability, you get a resilient sustainability index based on that look. So I just want you to focus on this one. There are tools to quantify the sustainability, but be careful when you are using these tools. There are some simplified tools. Like if you use a tool, carbon footprint analysis, that is not enough. You need to be looking at a broader, all the environmental impacts. And you look at the costs, not the direct costs, but the indirect costs and the indirect benefits. Don't ignore the social sustainability. And resiliency is ignored. So if you look at simplified methods that are commonly used, they have all these pitfalls. So you be careful. So the take-home, this is my last slide. So take-home message is sustainability and resiliency are extremely important. If you don't know about them, educate yourself. Educate, if you are in a company, educate your staff. If you are teaching, make sure that you teach students, in the courses that you teach, or develop a new course and teach them. Avoid greenwashing. Just, don't just use the word sustainability and resiliency. I see a lot of people using in the paper titles, thesis and all those things. But if you are used in a thesis or paper, quantify, show some numbers to say that it's sustainable. And learn different quantification tools. There is nothing wrong in learning something new, and know the limitations of each tool. And simplified methods could be helpful, but they could be giving you misleading results. As I told you, it may be carbon footprint point of view, it is maybe low, but you may have other environmental emissions that are high. So you just based on the carbon footprint, you cannot say it is good. So there are tools that integrate the resiliency sustainability, and they are more comprehensive. I recommend you to learn these things and use those things. So I want to thank organizers for coming up with this special issue of Indian Geotechnical Journal. That paper is there. And I want to inform you about the second edition of my book. Please, if you don't have any background, look at this one. And I want to thank Professor Agnihotri for inviting me, and all the entire organizing committee for doing an excellent job. Finally, I want to thank my graduate students. So this is my contact information. I can provide you more information during the breaks.
Thank you, sir.
Thank you very much.
Thank you, sir. Excellent presentation. Due to shortage of time, we won't be able to take up any question. And
sure, I understand it. So I know we are.